Good afternoon, colleagues and participants. Welcome to this technical session that we'll have at this second part of the afternoon. The session will be focused on the uh, topic informed decision making for agriculture interventions and irrigation decisions. I'm honored to be the moderator of this session, which will delve into some cutting-edge advancement and innovative projects aimed at enhancing agricultural productivity while addressing sustainability and water management challenges. We have in the program 5 presentations, but one of the participants, I think, experienced some difficulties to be present with us today, so we will have 4 presentations in this session. The goal of this session is to explore how technology and data can help and support us to address some of the most pressing issues facing agriculture, such as food security and sustainable water uses. The first speaker in my list is Jorge Guterres from the FAO, Food and Agriculture Organization. And the presentation will be on the program called VAPOR project, which uses a publicly accessible near real-time database to monitor agricultural water productivity. Jorge Guterres, the floor is yours.
Thank you so much, colleagues. It's a pleasure for me to present today the WAPOR project. This project is a project of FAO and stakeholders for 3 institutions research. This project began 2 years ago, and for Latin America and especially for Colombia in the last year. The project is very interesting because have a dialogue with this kind of issues. Over 200 million people suffer for hunger. Around 3.2 billion people live in agricultural areas with high to very high water shortage of scarcity. Agricultural production needs to grow globally by 50% to 2050 in our informed to state of the world and water resource. And from 2000 to 2018, total cropland increased with 63 million of hectares. Almost 85% of this increase in the irrigated. In general, this project use information about remote sensing for water productivity. That is an indicator that can be used to monitor, at the same time, progress and spatial variation in terms of land productivity, biomass, and yield. And in water being consumed to obtain these yields, both terms of equation are important and need to be looked at together, making the most out of every drop of water is a target that makes sense across scales and across water users. The project was founded by the Netherlands and has 2 main partners. One institutions, one of those is INVI. There is two colleagues here. It's a pleasure to meet in person. And the IHE Delft, that is an institution of education, water, it's important in the world and is a UNESCO institution. And one service provider called ELIF. From satellite images, our algorithm calculates parameters of interest such as biomass, evaporation, and precipitation, as well as other climatic parameters from which we can calculate water productivity and do water accounting at the basin level. That is very important for some researchers. The WAPOR portal provides data in near real time. What it means, every 10 days since 1909, we have 3 spatial resolutions. Fortunately, today we have 300 of size of pixel for all the globe. For some countries, we have 100 size of pixel, and in some cases for each countries, we have 1 or 2, or in some cases 3 analysis for 20 meters. And I invite you to show in each country what kind of measurement you have, no, in your institutions. Really, these are very, very good information disposed for the project and for free database. Okay, this is like you can see in the third level, that is subnational level, no? 20 meters for size of pixel. Okay, what is the data in the database and in the portal? Now we have water productivity, actual evapotranspiration, reference evapotranspiration, precipitation, relative root zone soil moisture, that is new, net primary production, and some quality layers. And the temporal resolution is very interesting because we have decadal, each 10 days, monthly, and annual time steps. You can see now in Colombia for South America. It is very interesting for our Latin American, Caribbean countries, because in this way, for example, the institutions and partners are translating the information and the course and the manuals to Spanish, and it's important for our region now. Okay, this second phase began in 2021, focuses only on the expansion of the spatial and temporal coverage of the database, but on supporting countries so that they could use web or data to capacity development and of tools or solutions together to respond to challenges that the countries themselves identify. This is very interesting because, you know, in each country there is a research in particular or have a special difficulty, and then we use in each case some road different when depends of the what is the research, you know. Okay, and I say WAPOR is open data access. What it means, have a methodology documents, manuals, quality assessments online. You can to download each document, each process. We have the codes and algorithms online. We do trainings to our countries. you can to see data and metadata available in the portal, and you can indeed navigate the portal. You maybe in this moment have two versions, the two version and the third version now with some variables in use. And as I say, we have open geospatial standards, and you can use all this kind of information for your context. In the same way, there is available resources for capacity development. We have courses, all the database in GitHub, and we use Python for the programming. And now the idioms, English, French, Arabic, and indeed Spanish. You know? Okay, what is the main idea of the use? We are talking about the different scales. Policymakers is one of these, because the idea is to understand where and, for example, in which kind of crops use this information. The second one is the irrigation schemes managers in basins, for example. And finally, and it's ideal to find farmers and identify end users for develop apps. For example, in another countries, there is like 6 or 7 apps that can be used the farmers directly. Some applications, in this case, we use this image to share performance indicators to understand variability, and you can separate each variable and analyze, for example, in this case, a specific basin and to identify what happened with the field production and the water productivity in some special case. It depends of the research, you know. Another application, we have this gift using in Mali irrigation Niger information, and shows the evolution of water consumption between 2009 and 2018. And it's interesting because in this case is in the better scale, 20 meters. Finally, I show some application in Egypt, Lebanon, Tunisia, and Jordan. It's another case. We developed AWP application, for example, for using the data, and no less important, to help the countries to measurement the SDG indicators 6.41 and 2. And in our case, in Colombia, for example, we are very focusing in drought because the El Nino phenomenon in these days. Now you can see Colombia and Africa in this kind of assessment. This is an animation about this relative root zone soil moisture that evaluate upper 200 centimeters of soil, making in the vital of the plant growth and ecosystem health. Some phases in the training workshops, and the idea is that you can see and navigate and download the manuals and database and make your own questions for the data portal. Thank you so much.
Thank you, Jorge, for this presentation. I think Vapor is one of the most important project that was initiated and developed by FO, and as it was demonstrated from the examples shared during this presentation, there is a lot of applications, a lot of impacts that this kind of application could bring to the agricultural activities. We can maybe open the floor for one or two questions from the audience on the presentation before moving to the second presentation in this session. Yes, please.
Thank you very much for the nice presentation. I'm curious about something very small. Why the resolution changes from country to country?
It's a decision of the project because we need to prove and to understand what happened with some special cases. Really, we are understanding and learning what happened with this kind of basin or latitude and longitude. Yes, we try to understand what happened, but in general, the most important is all the globe have 100 meters, and 30 countries have 100 meters. Okay.
Yes, one more question.
Buenas tardes, mi nombre es Eddie Romero de Costa Rica, Senara.
Good afternoon. My name is Eddie Romero from Costa Rica, Senara. The possibility of implementation in Costa Rica of the program with FAO, what is required for that? That question has been made previously. For the colleagues that are in Latin America and the Caribbean, we have a regional focal point and one in Mesoamerica, in Panama, and we are making the dialogues and expanding the resources that are available. They go all the way to 2025, sorry. So what we're doing is we're starting to expand the trainings. I think that very surely the growth of the use of the application will go somewhere there, which is already an advantage for us, the Spanish speakers, that the course now has. For example, it is now open in Intel and it is in Spanish, and you can download it, you can do the courses without any problem. So we're going to have the biggest possibility of working on that.
There's a very famous movie called Lost in Translation.
Y hay una muy buena película que dice Perdido en la traducción. ¿Puede resumir para que todos los participantes puedan también responderlo? Nuestro colega preguntó.
For example, if we in Latin America, how can being the route to implementation, and I say that exactly there is an advantage now because for Hispanoparlant, we have now in HEDEL Spanish course, and it's free and can to download and to join to the course. Excuse me for switch to Spanish.
Yes, please. Do you have a question? Yes, please. Here. Okay.
Hola, hola. Sí. Muy interesante tu presentación, de verdad, me gustó mucho. Muy
Your presentation very interesting, very precise and simple.
Voy a hacer la traducción.
I'm going to do it in both languages. I would like to know if the application is a FAO or is it a group free, and can you adapt it to multiple platforms or devices?
I love your presentation, very high quality, very precise. I want to know if your application is free or we must pay a fee for using different platforms or for different users. After my question, the lady.
Thank you for your kind question. Yes, this is a frequently a question when we present WAPO, because you know the use of another kind of information is for pay, no? Now precisely the advantage for WAPO is that the information and the database is it's an open access database. You can use the data that is available for the countries. I say for Colombia in Latin America and Caribe is information by 100 meters for the pixel size, and for African countries and Middle East is in some cases for all the 12 with Colombia countries available in this size of pixel, no, and it's for free. It's open access database.
Just a quick clarification for the answer to the first question that was asked. You said in general, all over the globe, there is a 100-meter resolution, and in 30 countries there is?
300 meters of resolution all the global.
Okay, thank you.
Yes.
And in 30 countries, it's 100 meters.
100 meters.
Perfect, thank you.
Maybe last question from this lady.
Thank you for your presentation. One thing struck me, you said there's action-oriented data for different users. And you gave examples of farmers, as well as, I think, irrigation scheme managers, and also decision makers. So I was wondering how that information or data is made accessible, one, but is understood by all these different users. You know, how is it communicated to them so that it is action oriented for all the different users? Because the understanding by each of the users would be different.
Thank you. Good question. Yeah, this is the main challenge. You take the point, because it is easy to bring, for example, training for experts, no? But you know, our farmers and maybe the decision makers don't have this kind of expertise. But the challenge is how to put it together in a dialogue table of interchange of knowledge. There is the challenge of each coordinator by country. In my case, in Colombia, for example, in my case, we do training workshops both, no, together, and it's a challenge.
Maybe to bring some complementary information to your question. The system is providing different kind of indicators. Some of them are used by farmers and some are used by decision makers. For example, when it comes to the water productivity is something which is more used by decision makers to know if it's worth to invest in irrigation in this area, knowing that the productivity is low or high, etc. This is information which is dedicated to a decision maker, for example. When it comes, for example, to managing irrigation at the farm level, for example, water consumption is one of the information provided by this system, is more easy to use by farmers than by decision makers. So the system is providing a list of indicators which are different with different information, and each component or each group of these indicators is used by different kind of users. Could it be decision makers, farmers, water authorities, etc.
Thank you for complimenting.
Yes, please.
Thank you. Who was your process to validate the actual evapotranspiration in Colombia? And the other question is, what was the approach to estimate the different variables to relate it with actual evapotranspiration? Was the for energy approach or mass approach?
Yeah, thank you so much. Because you touched the validation process, and it's very important because we are talking about the reduction of uncertainty, no? Yes, there is a process in the between the L2 and L3 layer, And if you can to access to L3 layer, you need to take data in field. Yes. And the focus of evapotranspiration is the FAO focus biomass.
Well, once again, thank you very much for your presentation and from the questions raised by the audience. I think subject is very important and there's a lot of interest in this discussion. The second presentation speaker in this technical session is Mr. Karchikian from CGIAR, and he will present presentation on the sustainable agriculture in the lower Limpo Basin, focusing on irrigation performance in Mozambique. Thank you.
Thank you. Thanks, Jorge, for setting up the scene. Basically, we are working in the same project, but in different countries. So my presentation is basically a continuous, Jorge's presentation. And there were many discussions about how the data sets that are available in the portal could be potentially used for some specific applications. So the work I'm going to present is a specific applications that has been currently implemented in Mozambique using the WAPO data with the stakeholders. Yeah, we all know the challenges ahead in terms of the irrigated agriculture. Like we have been discussing from the morning about the challenges of optimizing the water use within the agricultural system, and Mozambique is even not an exception. They have a unique set of challenges in terms of, for example, Mozambique is one of the downstream countries in the lower Limpopo River Basin where they are subjected to floods, but in case of the upstream countries, floods are not a major issue, but droughts are the issue. And Mozambique has invested quite a lot on irrigation infrastructure, particularly in the lower Limpopo River basins. But then these irrigation schemes have undergone a lot of governance in terms of, for example, these were set up as primarily a public irrigation systems, but then in between it has changed to smallholder systems. Now it's a mix of both public irrigation as well as smallholder irrigation systems. And now there is again a further change in terms of moving from for example, they are renting out a lot of irrigated areas to big private companies. At least 50 to 70% of the irrigation schemes areas are rented to the private companies, but then the remaining 30 to 40% schemes are still under the smallholder systems. So there are a lot of governance challenges and the way in which the governance is also evolving in these irrigation schemes in Mozambique. And of course, because these schemes are spread over 40,000 hectares in the lower Limpopo, there is currently no monitoring system in terms of how these irrigation schemes are performing in terms of its intended objective when it was designed. So when we started working with different stakeholders in Mozambique, so the way in which the FAO, for example, the WAPOR project works is that we go into the specific country and we interact with the different stakeholders in the specific countries, including different government institutions, private sectors, universities, and research institutions to identify a broad set of challenges that could be potentially addressed using the WAPO data sets. Once we identify a broad set of challenges, usually when you ask them what are the specific challenges that you need to be addressed at a country level, then you get challenges which may be addressed using WAPO data and which may not be addressed using WAPO data. Then we try to prioritize a specific water resources challenge that we could address using the WAPO data portal. And we try to engage with the relevant stakeholder who are responsible for addressing that specific challenge. For example, in terms of this specific case study in Mozambique, when we identified that the stakeholders are interested in assessing the irrigation performance of these big irrigation systems in the lower Limpopo, we identified two stakeholders within the Ministry of Agriculture. One is INIR, which is responsible for the irrigated areas in the lower Limpopo, and then the second one is the irrigation scheme managers. The irrigation schemes are now in quasi-government entities in the sense that it's both government as well as public. So private, so they've got a 50% share in that. So these are the two primary stakeholders we are engaging now in terms of co-developing this tool. Jorge mentioned about this WAPO database. Just to sum it up, his presentation, WAPO is basically a database which provides you a free access to a land and water productivity indicators. When we say land and water productivity indicators, there are two primarily important data sets in the WAPO portal. One is the crop water use data, which tells you how much water was being used by the crop. And the second one is the net primary productivity data, which basically tells you how much carbon has been assimilated in terms of production of the crop. Essentially, you can convert this net primary production into an biomass production. That means the crop yield. So in essence, WAPOR provides two critical data sets. One is how much crop water is being used. The other one is how much crop is being produced, right? In essence, that's what the WAPOR data does. And you also have another, what we call as different indicators like precipitation derived from CHIRPs or reference CT derived from, for example, the FAO portal. And there are different data sets which are derivative of the other data portals. And these are made available at three. I think there was a talk about the spatial resolution, why the spatial resolution changes over different countries. So for the global, the spatial resolution is 300 meter by 300 meter. But then for specific countries, it's 100 meters. And these specific countries, the whole of African continent is covered by 100 meters. And there are a couple of countries outside the African continent, particularly Sri Lanka, Pakistan, and Colombia are covered by 100 meters. But then there is a third level of data set, which is the highest resolution of the data set, which is the 20-meter resolution. And that is being covered only for a very, very small focused area within each of these countries. For example, in Mozambique, the entire Mozambique is covered by a 100-meter data set. So whatever the data sets that Yoge has listed is covered for whole of Mozambique at a 100-meter resolution. But then for the specific areas where we are focusing on the lower Limpopo, it is covered using 20-meter resolution. And the reason is that because of the cost, right? All these data sets are processed in the cloud, and there is a cost associated with processing these huge high resolution data sets at a country level. Unless there is a specific need from the stakeholders, it is extremely prohibitive to process this data set for country level at 20-meter resolution. That is why the data sets are available at 300, 120-meter resolutions for different levels. Again, these data sets are available at different temporal resolutions. One is decadal, every 10 days, monthly, and then yearly time scale, right? So this is second phase of the WAPOR project. The first phase mainly was like a proof of concept phase where the portal was developed and we tried to pilot 1 or 2 applications. The second phase focused primarily on how this data could be used for operational applications in different countries. And these are the sort of a bottom-up approach where, for example, the FAO basically is in charge of the overall project and then developing and maintaining these databases, while IHE focuses on capacity building activities, and EME International Water Management Institute, where I come from, focuses on developing a specific stakeholder-centric applications using the datasets from the WAPO portal. And at the moment, we are working on at least 11 countries as of this month, working with different set of stakeholders, developing different type of applications, including some of the mobile apps that Yoge has showed in his presentation. So our scale sort of moves from national scale to farm scale. In the farm scale, most of the times our focus is on irrigation scheduling, which is being piloted in Palestine and then in Tunisia at the moment. But then in a number of other countries, our focus is on a system scale. We are focusing on specific irrigation systems like what we are doing in Mozambique. But then in other countries, we are also looking at the national scale, looking at for example, the water accounting and about water budgeting aspects of it using the WAPO data. So basically the way in which we approach this is once we identify a specific solution, specific challenge to address and specific stakeholder, we organize a series of meetings with them, try to co-develop these solutions in terms of what they expect from these solutions. So instead of we trying to sort of create a solution for them and giving it to them, we ask them, okay, this is a challenge you want us to address. And this is these are the data sets available in the WAPOR, how we can go about it. So what sort of applications they need and what sort of outputs they expect from it. And then we have a series of meetings with them. We try to co-develop it and brainstorm it. And then eventually we come up with some sort of a very skeletal framework which looks at this. So basically this is performance indicators that we derived from the Mozambique stakeholders for this particular applications. So when we are looking at this irrigation schemes, most of the common indicators, for example, focuses on the crop water use, how much water is being used by the irrigation scheme. And then they also need an information on the crop water requirements, economic water used, basically the economic water productivity, system efficiency, right? And then crop type mapping. We have to note that not all of the indicators could be eventually derived from the vapor. Some of these indicators can be derived directly from the vapor. Some indicators need field level data sets. Some indicators, for example, crop type mapping, need a separate level of activities, right? So then we basically try to identify what sort of data sets that are available with the stakeholders, and then we try to develop these indicators. At the moment, we are focusing on developing the crop water use side of analytics and how this can be scaled up to a number of irrigation scheme across Mozambique. So this is basically the framework in terms of how the tool will extract the data from the vapor portal automatically using the API, and then it will create a set of remote sensing based indicators. And then also when we get the data from the stakeholders, it will combine the remote sensing based data sets with the field based data sets to derive indicators in terms of the system efficiency, in terms of, for example, the trends in the crop water use, the seasonal water use, or even annual crop water use. So at the moment, we are looking at 10 irrigation schemes with combined area of almost 90,000 hectares. But at the moment, in this today's presentation, I will just show some of the results from the Chokwe irrigation scheme, which is the largest irrigation scheme in Mozambique with 40,000 hectares. As you can see, Chokwe irrigation scheme is basically located in the lower Limpopo basin in the southern part of Mozambique. And it's around 40,000 hectares. It consists of sort of three sectors and then multiple blocks within it. We did not go into the farm level water use before because at the time the resolution was at the 100-meter resolution. The level 3 resolution was not available, so which was not really suitable for the farm level applications. But then now the level 3 data, which is at 20-meter applications, are maybe 20-meter data sets are made being available. So we are basically moving beyond the block level to the farm level water use. Now, instead of 3, we are moving to the 4th level of water use, which looks at scheme, sector, blocks, as well as farm level. Again, one of the requests from the stakeholder was that since this is a quasi governmental organization, they are being charged by another organization for the water use. But then they don't have any specific estimates of how much water is being used within the irrigation scheme. By employing the vapor data, we provide them how much water is being used within the irrigation scheme on an annual basis so that they can compare it with the organization they are charging the data sets for, right, in terms of the amount of water used. So this is a seasonal water use in terms of the annual time scale. So you can also look at spatially how the seasonal water use sort of changes, evolves over the time period. Sorry, this is from 1920 to 2020-21, and we also have most of the recent data sets available. Again, you can look at the seasonal water use in a very, very different way. So, for example, whether these water use are distributed equally among the different locations of the irrigation schemes. And you can see that when you look at the equity of the water use, most of the times the water used, the equity of the water use is generally poor, but except in one instances where it's generally fair, it means that the irrigation scheme is not yet performing to the optimal level. Again, it's another indicator in terms of the beneficial fraction. Basically, beneficial fraction looks at when a certain amount of water is being used by the crop, how much is the transpiration component of it, and how much is the total ET component of it. It just looks at the ratio between the transpiration and the ET component. And you can see that it's generally within the acceptable limits. We can also see the trends in the biomass water productivity. Again, we just need to be a little bit careful about looking at the biomass water productivity because without the crop type information, the biomass water productivity will not give you too much of an indicator. But what you can see is a sort of a trend within these 4 irrigation seasons, and suddenly you can see that one irrigation season sort of having a downward trend. Again, this is the type of analytics that you get from the remote sensing, in the sense that remote sensing tells you that there is certain type of trend going on, whether increasing, decreasing trend, but it doesn't tell you why. Maybe it's because there is certain flood event that has happened during that particular time that led to basically destruction of crops in the lower Limpopo, and that basically being reflected in the lower water productivity and lower yield. So at the moment, we are trying to move the system from 100-meter resolution, which is what Yoke mentioned at a national level, to a high resolution of 20 meters. We're also trying to move from a block level applications to a farm level. So there will be a 4 level of applications looking at system level, at the scheme level, sector level, block level, and farm level analytics. And we are also trying to combine with the field-based also in situ information from the stakeholders in terms of estimating the canal efficiencies. And unfortunately, I couldn't show the canal efficiencies because which are sensitive for the stakeholders. So we basically estimate the canal efficiencies with them, and then they submit it to their senior management to get approval before we could show it outside. I conclude my presentation here. Thank you. So if you have any questions, I'm happy to answer. Thank you.
Thank you, Cartier, for this presentation. I think you are providing more details from the first presentation of abroad, the complementarity between these two presentations. We'll open the floor if you have any questions. Maybe I can start by asking one question. You are using different type of resolutions, but this data used for the 300 for 120 is not the same. And I think the system is based on thermal data. So how do you manage to get information at 20-meter resolution, knowing that there is no satellite providing the images with thermal infrared data at this resolution?
Sure. So at the moment in the tool, we sort of moved from 100-meter resolution to 20-meter resolution because that data was being made available for the Mozambique area. In terms of the 20-meter resolution, the best available resolution directly is the 30-meter Landsat, right? That's the best thermal resolution available. But in terms of this project, Vapor has developed a methodology basically to combine different data sources from Sentinel. So they basically take a Landsat base temperature from Sentinel, and then they use a machine learning algorithm to basically improve the Landsat base temperature to a Sentinel temperature, and then use a Sentinel data sets to derive 20-meter data sets. So it's basically a combination of Sentinel-2 data set as well as Landsat data set. That's where you get a 20-meter.
One time question concerning the validation. When it comes to this level of precision, which kind of processes you are using to validate data, and what is the quality of this validation or the accuracy of data at the end of the process?
So the overall validation activities are handled by IHE Delft. So they look at the project level, trying to identify, they basically try to do the validation for a number of different countries as a project as a whole. But then as a part of a capacity building activities, we collaborate with IHE to do country level validation activities. But having said that, number of these countries don't have the necessary data sets to validate it. So when we go to these countries, most of them, they ask, how do we know that your data set is accurate? And I tell them, we don't know. That's the truth, right? But then I tell them that at the moment, the countries doesn't have any information on countrywide water use. So this is the first set of information that's being made available. So our focus is more on making them comfortable with use of the Earth observation data sets. So and then we do semi-quantitative validation, not full validation as such. So we try to show them semi-quantitative validation in terms of, for example, we calculate the potential ET, and then we have some crop-specific information to calculate actual ET based on the FAO Penman Monteith, and then try to basically compare these two actual ET evapotranspiration methods to see where it fits. And as long as the variations are not so much, then we sort of conclude that it's reasonable, within reasonable amounts. But there are some countries where flux tower estimates are available, for example, in Jordan, where we do full-fledged validation activities. Again, IHE does the full-fledged validation activities. So it purely depends on the countries. In some countries we do, in some countries we just purely stop with the semi-quantitative validation.
Yeah, and in countries, when you have this kind of data available, what is the level of accuracy you are reaching?
Again, to be frank here, it depends on specific crops. For some crops, and that's been the challenge with all the energy balance model, right? For specific crops, the accuracy is up to 85%, right? The actual ET is reasonably accurate. But then for some crops, it goes down to 60% of accuracy, right? So I have to also acknowledge that there is huge uncertainty with the use of remote sensing data set, and the uncertainties could come from multiple aspects of it. For example, Vapor uses purely global data sets for the energy balance model. And there was a talk about how the ET is produced. The ET is produced basically using an energy balance model, but then the weather inputs that goes into these data sets are all global reanalysis data sets, right? Which are not specific country level or in situ data sets, which has got its own uncertainty. The soil parameters that goes into the model is again a global data sets, right? It's not customized for a specific locations, right? There are uncertainties associated with it, right? One of the things I do recommend, again, as I said, that we emphasize on comparing the relative differences. That's what we are trying to do with the irrigation performance. That's why if you look at the out of 11 applications, we have at least 4 or 5 applications of irrigation performance, where beyond the magnitude of the specific specific variable, what's of interest to the stakeholders, or how one portion of the irrigation scheme performance better than the other performance. So the moment we go into the relative performance, then your magnitude value becomes a little less important.
Okay.
So, yeah.
I don't know if you have any questions. Yes.
I'm not sure if you use temperature in your process, in your algorithms to correct some part of the process.
So there are bias correction methods in terms of using the, for example, there is bias correction approach implemented by the ELIF. For example, the entire processing chain and the data sets development are implemented by ELIF, the consortium that part of a consortium that UK has developed, right? So they run this standard processing chain and then they produce these data sets, and then FAO basically coordinates with them to make sure that these data sets are available. And then IHE basically takes care of the capacity building activities, and we basically try to develop this tool. But then temperature is actually a part of the input data set, but I'm not sure. There are bias correction methods implemented in terms of correcting these temperatures or some of the weather variables that goes into these models, but I'm not sure what exactly.
No, it's because it's very important variable when you want to estimate the actual evapotranspiration. Yeah.
Yeah, but we don't have access to the in-situ data sets, right? Getting in-situ data sets, access to in-situ data sets from meteorological agencies are still very difficult at a country level, right? And it takes time. And for near real-time operating systems, like for example, this one. So for example, every 10th, 1 to 10th, you have one data set, 11 to 20, you have second data set. And so 20 to 30, you have third data set, right? So for example, that's what we call a decade. When one decade ends, within the next 5 days, the data set will be available for that tree, for that particular decade, right? And there is no time, or the time frame is not suitable for us to get access to these data sets and then implement this specific, or tailor this model specific to a particular location or a particular country. And I can tell you, I don't want to name a country, but I tried to access the meteorological data. They quoted me $40,000 for 4 stations. So
Okay.
Okay. Thank you.
But maybe
I think the discussion is very interesting. Just allow me, please, because we have two speakers online, and they are from Europe and Africa, and it's too late in these countries. So we can go back to the discussion after the two other presentations we have on the schedule. Thank you.
Sure. Thank you.
We'll rapidly move to the third presentation in this session. And I will call Francesco Volo from the University of Natural Resources and Life Sciences in Austria, who will present the Koala API, a cutting-edge solution for space irrigation scheduling. Francesco, you have the floor.
Yeah, thank you, Mr. Chairman, for facilitating the move to the European time. It's pretty late here. Thank you. I will try to bring another example of how remote sensing data is being used for doing irrigation management. And in particular, we talk about the Koala Enabling Platform, which is a system to produce operationally irrigation advisory information at farm scale. So we primarily work at 10 meter spatial resolution, so it's one pixel size, and the focus is exclusively on the farm, perhaps also on the district scale. I will give also a brief introduction of the different changes that along my career in this area I've been observing. And we can obviously say that there's been improvement in the ways irrigation water is delivered to the fields. So there's been a lot done in that area, but there is also a lot being done in the way agro-meteorological parameters are measured in the fields with the availability of automated weather stations. And we see more and more sensors placed in the field, IoT, but also climatic models that provide, for example, in this case, precipitation data at a quite detailed scale. One of the main problematic we've seen is that there is a mismatch between the scales at which data are provided, for example, from climatic models, from sensors placed in the field. And lately, also from satellite observations. And one of the things we see is that data we get, for example, from Sentinel-2, from Landsat-like satellites, they very much represent the variability that we see in the soil. So for example, in this image, we see a Sentinel-2 scene. In green, we have vegetation in brown soil. And on the right-hand side of the screen, we see a soil map of this area. And we see that these spatial patterns are quite well represented in the image. When we look at, for example, rainfall data, they come for this particular region. We're talking about Austria in Europe. They come at 1 kilometer pixel size, which is clearly too coarse, too large to do any management at field scale. On the other hand, farmers also invest in placing sensors in the soil, but those sensors represent very often a variability in area that is too small, too limited to do management. And the data such as Sentinel come at the right spatial and temporal resolution to really support farmers in irrigation management, irrigation scheduling, understanding of the water requirements of the crop. One of the parameters that at the moment we can best measure with very high confidence from Sentinel-2 like satellites is the leaf area index. And in this slide, in this time series, we see on the top different parcels, in particular irrigation pivots, how this changes color across the season, and this represents the leaf area index. So it's one of the major parameters used in the estimation of the crop evapotranspiration, in particular based on the FAO PEMA-mounted approach. And today I can confidently say that this parameter can be very well estimated. An example of how Sentinel-2 in combination with reanalysis data or climatic model that provide the classic climatic variables such as solar radiation, temperature, wind speed, and precipitation. In combination with those data and Sentinel, for example, using the PEMA-mounted approach, here we have an estimation of the water balance across the time, so weekly understanding of the ET, the rainfall, and the aggregation of this data for different periods of time to look at irrigation scheduling or water consumption across the season. Qual has been implementing these approaches into a complex system that can manage the different data sets, the different methods, and provide data to the users. So let's have a look at how this works. So everything is implemented in a cloud computing infrastructure where climatic data from models, satellite data from Sentinel, Copernicus, in some occasions also field data are gathered together. So cloud computing can be on Google Earth Engine, can be on one of the European processing services related to the Copernicus data sets, where we also place an orchestrator, so a machine that can handle the data flow, inflow and outflow, but also activate dedicated processing, for example, to do atmospheric correction, to retrieve leaf area index, and to look at value-added products such as evapotranspiration and the aggregation of this value across spatial and temporal scales. The connection then to the users is done via API. I think this is a common technology today, so I probably don't need to go too much into the detail of that. And we imagine in our workflow an intermediate figure, character that takes the data via the API and present this data to final users, such as farmers, irrigation infrastructure, or authorities at district scale, and the data packed together, graphically formatted, to be used by these final users. So Koala is not dealing or talking to farmers directly, but via intermediary company is preparing the data and delivering those data. In this presentation, this talk, I'm particularly focusing on the Koala irrigation services, but there's been done more. Particularly, we've been looking at fertilization services as a bit of package of precision agricultural tools. So fertilization has been another big topic, for example, to derive management zone maps or looking at the nitrogen nutrition indices and so on. But again, coming back to us, evapotranspiration is one of the major products. Knowing the precipitation, we can look at the crop water requirements and also provide an indication of the soil canopy water content. And again, all this is done by using Sentinel-2. Because in our experience working across different areas, mainly in Europe, this satellite Sentinel-2 provides the optimal temporal and spatial resolution to address most of the management, the crop types and field size that we have in our regions. Let's have a look at what this orchestrator in the cloud computing infrastructure is doing. So we have some regular processes that happen as new data are coming. So for example, a new Sentinel-2 acquisition is obtained, an atmospheric correction is performed, leaf area index albedo fractional vegetation cover is derived, the clouds are masked, and those data are stored into a database, and they remain there until the moment a user is requesting, for example, an irrigation advice or crop water requirement estimation. At this time, an on-the-fly processing is activated, and the previously calculated leaf area index and albedo, for example, are used to, in combination with climatic data, to get ET, so evapotranspiration. And the provision of this data is also done on an adequate temporal scale, for example, by doing a daily time series interpolation and gap filling, so that for every day, even though we don't have Sentinel-2 data on every day, we can provide such an advice. And finally, the information is decoded or simplified into some of the terms commonly used by users, so ET, crop water requirements, and their spatial aggregation. So this division of regular and on-the-fly processing is done to mainly optimize cost of processing and resources use. This is a quick example of how this works. So there is a base address, API Koala, and the number of parameters that users or intermediary providers can adjust. So for example, the coordinates of a point of interest, the date of interest. Let's say we want to have ET for now for a period of 10 days, and we want to have an image returned, and this information is provided. We've been talking in the previous presentation about validation, and being a scientist, this has been at the core of my work, of my interest, and the parameters that we believe are the most realistic to validate across years and spatial scales is leaf area index that we have been extensively validating using the plant canopy analyzer across different crops. And the other variable that we have been also extensively validating with more pain and more work has been the evapotranspiration via the direct comparison with eddy covariance derived ET data across, again, different years and across different crops. There's also been a comparison. This is a particular example for the application of Koala in Australia with alternative data sets, and this is the TERN, which is actual evapotranspiration derived using thermal data from the Lancet mission. And you can see here a comparison between the ET derived from Koala on a monthly average and the ET derived from TERN on a monthly average. And also in this case, we see a good correlation. The interest for Koala was also to look at providing operational services. And as you have seen, some of this processing happen on the fly, and we don't want users to wait. And therefore, we have also optimized the way all this processing is done. And here you have an example of the response time. So if you submit a request now, you want to get ET calculated, let's say, for last 15 days or longer. And this is an example of a calculation across a period of 50 days, and it takes about a second or a bit more than a second to obtain DT for 1 point across about 2 months of time. And then on this point, on this aspect, we've put a big effort. So Koala has been also extensively demonstrated with third-party companies that provide services to farmers. That was a bit our approach. We don't go to every and each farmer to demonstrate, but we use these well-established institutions that already have a pool of users, of customers to do the validation. So, for example, we have been talking and integrating with eProfit in Australia. We are currently using Koala to provide data via this Map Timer Explorer in Italy. Colleagues in Spain have implemented their own web interface to activate Koala processing via the Koala API. Schedule It is another example of of provider of services in Australia, particularly for scheduling irrigation. And finally, we also been working on creating a plugin for Quantum.js so that you don't need to know complex scripting and your, let's say, Python or R interfaces to derive data, but you can simply use a plugin, and this should simplify the way to obtain data. So what we believe is the innovation and the value. In my opinion, the value is that this data can now be derived, or these products can now be derived very fast, while still maintaining the quality and the accuracy that 10 years ago was derived by having manual expert operators performing, for example, the atmospheric correction, LAI retrieval, and so on. But everything now is automated. And this means that the process is more efficient, the accuracy is maintained, and having such a system at the background means that we can now focus on talking to more users and scale and customize everything, and as a result also save the cost. And the vision is that saving costs, you can go to more users and have this technology adopted on a larger scale and more benefit for everyone. So Koala is a private-public initiative that has been initially funded by the European Commission through research funds. And we are now, the project was concluded in 2023, so last year. And we are now in a phase of searching for additional fundings, additional users, additional demonstration, so that we can continue the operation of such a system and perhaps the further improvements of the services. And therefore, we also provide Koala on a project-by-project basis for scientific use, but also for demonstration if there is a user at the ground that is interested in using it. And you can ask to me directly for an access to it, but you also have online documentation. You will find a reference in this presentation where you can look at the technical documentation or the easy access through some ready-made templates to obtain data for Koala. I thank you very much for the attention and the opportunity, and I'm very happy to take questions now or also online. Thank you.
Thank you, Francesco, for this very interesting presentation, and also thank you for being patient and waiting for us very late in the evening in Vienna, but I think it works that you are sharing this very important project and very promising results from this project. And maybe we can have quickly one question, then we can move to the next one. Yeah. Yes, please.
In your presentation, you mentioned that 10 series data smoothing, that is a very important step to make monthly data or several days data to daily. Can you say more few words about the principles of this kind of data smoothing or the
Yes.
method? Thank you.
Yes. So climatic data today, they come already on a daily time scale. So this is not a problem anymore from climatic models. While Sentinel-2 Landsat data, because of clouds, because of the revisit time, they come at, it's in the optimal case, at 3 days temporal resolution. And we need to bring those at daily temporal resolution. And we use different algorithms. We use, in this particular case, we use an algorithm called Whittaker, which is a function that helps you to interpolate in between observations. And we have optimized it to run on a data cube so that it can effectively and efficiently provide daily data on a certain time interval. The process is quite complex to go into details, but it has been published and documented on how we do it.
Thank you. Maybe we
Thank
can
you.
take questions later. Then now we will move to the next speaker in this session, who is Mr. Mohammed Fawzi Smij from the Royal Center for Remote Sensing in Morocco, and he will be sharing with us a project that was developed by the CRTS called Irrigation Morocco. Smij, you have the floor.
Thank you, Mr. Chairman.
I assume that you are trying to share your presentation. Okay.
Okay. Yes, thank you, Mr. Chairman. I am pleased to be here with in this conference to share with you some experience.
Maybe you can change your presentation because we have also your notes as well as the.
Okay. Go. Mm-hmm. It is correct, no?
Yeah, it's okay.
Okay, thank you. Thank you, Mr. President. First of all, I would like to thank the organizer for giving me the opportunity to present our work carried out within the framework of the Irrigation Morocco project, whose title is Operational Irrigation Management Based on Remote Sensing. Like many countries in the world, water resources in Morocco is in difficult situation due to climate change. Thus, water saving is the first priority in the new water policy in Morocco. In the agricultural sector, the strategy to safeguard irrigation water involves better management of use of irrigation water, promotion of localized irrigation techniques, and rationalization of groundwater use. In this context, the proposed project Irrigation by CRTS was labeled by Space Climate Observatory in 2022 in partnership with French laboratory CESBio, and local partners OMVAG, Irrigation Water Distribution Office in Gharb region, and National Institute of Agronomic Research INRA in Kenitra. It is well known that estimating water consumption and needs from satellite image goes through a modeling process. Two families of approaches were used. The first is based on the energy balance, and the second uses the water balance. Our projects use both approaches and tries to find some synergy between them. The projects generate indicators and advices on water consumption and productivity at different spatiotemporal scales. CEBAL approach uses both VIRS data and Landsat data, deals with watershed, irrigation parameters, and plots spatial scale at daily or 8 days frequency. The water balance approach, called SATIR, is more used for plot scale. The energy balance approach in the IRISAT project is divided in 3 components. The first one uses CEBAL model to generate actual evapotranspiration, soil moisture, and biomass from Landsat and VIRS data in conjunction with meteorological and ancillary data. The second module generates indicators on water consumption, water deficit, water productivity, and irrigation advices. The third module concerns dissemination of this product to users. This table resumes generated indicators definition, their production frequency, and end users. There are 3 groups. The first group focuses on crop water consumption and deficit. The second focuses on crop production and productivity, while the third on soil water reservoir availability. At the same time, the project uses the SATIR platform based on the water balance approach. This platform is the result of the Franco-Moroccan collaboration through the LMI Turema Research Laboratory between CESBio and Qadi Ayyad University of Marrakesh. The goal of this platform is to advise farmer when and how much water to bring for the next 4 days. SATIR platform uses Sentinel-2 data at the plot scales to estimate crop coefficients and the fraction of vegetation cover, calculates reference evapotranspiration using the Penman-Monteith model, and establishes water balance to evaluate crop water requirements. The generated indicator by SATIR platform are actual evapotranspiration, water content at topsoil and root zone reservoirs, and next irrigation date and quantity. As an illustration of the product generated at the scale of the Cebu watershed, it is we show here the actual evapotranspiration at the resolution of 375 meters generated from VIRS data on July 10th, 2020. We show here the same products at the scale of the irrigated perimeter of Gharb at the resolution of 30 meters generated from Landsat data on date of February 11th and April 18th, 2020. Here, the slide shows biomass maps at the same resolution for the same dates, and here we show root zone soil moisture contents maps at the same resolution for the same dates. It is possible to follow the evolution of the generated indicators throughout the whole season. These figures show the monthly average water consumption and biomass evolution for all irrigated crops in Kenitra province. Validation work against flow measurements was carried out on 2 experimental plots of maize and olive trees in Shishawa. The figures illustrate the comparison between estimated and measured evapotranspiration. The root mean squared errors are 0.48 and 0.78 millimeter per day, respectively. To improve the CEBAL model, a crop map in the Gharb irrigated area was generated using machine learning technique, using time series of Sentinel-2 images during the 2022 and 2023 season. The main crops are cereals, citrus fruits, beets and sugarcane, greenhouses, fodder crops, and market gardenings, etc. To disseminate products, a prototype dissemination platform has been initiated at CERTES. This platform provides access to information on different territorial subdivisions, from the whole water basin down to the individual plots, depending on the user profile, from water basin managers, irrigated perimeter managers, to the farmer. And the example illustrates in the figure shows the farmer's access to the water consumption of his plots and its evolution over time. On the other hand, SysView has produced another prototype of a Satyr dissemination platform designed exclusively for farmers. After registration, the user provides information on plot location, crop type, sowing dates, and irrigation inputs. Throughout the decision, he receives information on water consumption, irrigation advice, and information on the condition of his crop and soil moisture. I will conclude my presentation with the next step. First, creating synergy between CEBAL and Satyr approach by continuing validation works and attempting to combining the models through assimilation mechanism. We begin this activity. The second step is generate products at daily frequency at 10 meters spatial resolution. Third, develop a unique dissemination platform. Fourth, test the system on a sample of farmers before transferring it to startups. And finally, generalize products on different Moroccan watersheds and irrigation perimeters. And this concludes my presentation, and thank you for attention.
Thank you, Mr. Smij, for this presentation and for sharing this, the results and the approach developed by this project in a very specific situation in Morocco, and also underlining the cooperation between two teams trying to combine two different projects on two different approaches to provide information to the end users. Maybe we have time for 1 or 2 questions to Mr. Smij, if there is any questions in the room. Please, yeah.
Thank you. The question was more on the, you were showing different end users. And I was thinking if the platform or the application will have different users. Say, I'm an admin, so I'm able to see these variables or this information. I'm a farmer, so I would see only these. Is that something that you have considered as part of the project or as part of new developments?
Yes, thank you for your question. In the platform, in the Irrisat, in the approach used global data, global scale. The platform for dissemination provide different profiles of users. For example, watershed managers have access to all the data for his watershed at large scale. Irrigated managers are access to scales from sectors, blocks, and all the irrigated perimeters, and farmer have access only on his own plots. This is the profile of users. Each profile of users has access to his own data and scales.
Thank you. So the other questions? Well, once again, thank you to our 4 speakers in this session. I think it was an opportunity for us to share different levels of experiences of projects, but I think this is a clear demonstration that satellite data combined by modeling is providing very useful and practical information, and also responding to different kind of needs and of end users' requirements. Also demonstrate that this kind of applications is easily transportable to different regions, to different situations. Viper, for example, project developed by FAO is now available at level country, for example. The project developed by the colleague from the Vienna University shows that there is a high level of value-added services that could be provided by private sector to different companies or to different users. And also the project from Morocco shows that on a national level, there is a possibility to develop a specific project that is tailored to the local needs. So I think from this discussion, we can easily conclude that the high potential of satellite data for irrigation management is demonstrated through these projects. And I think this may be a very promising perspective in the future, and also could be one of the topics that could be developed within the community in space for water projects to make these solutions, these technologies available and accessible to a large community in the near future. Once again, thank you to the presenters, and also thank you to all participants for this first day. And I know it's a very hard and long day, so mainly for person coming from far. But I wish you a nice evening and hope to see you tomorrow and for the second day of our presentation and our conference. Thank you.